Hello, community of sentence transformers. Today I want to show you something really nice. What we're going to do, we have a zero-shot classification problem. We install Pytorch, and I want to show you at the end of the day, when we run through all of the code, we will be able to say have a sentence like this one, and we'll give it a kind of label, and we will have a zero-shot classification with sentence transformer with SBERT. And I want to show this to you, but of course, we will also be able to have, where is it? Let's say we have a document, and here you have a document here, will be our demo document, and then we have a question and answer. And I will have then a question about the content of this document, and the system SBERT will provide me with an answer. And we will go with different lengths, so a question and answer and a zero-shot 4-sentence embedding. Yes, beautiful. So we have pip install our sentence transformers, then we have our Pytorch. Pytorch is up and running. We have here the 1.11. And what we're going to do is we have a look at transformers, at attention and multi-head attention. And the first thing we're going to do is we're going to learn about cross-encoder. And you might say, what the hell is a cross-encoder? Now, the beautiful thing here is a cross-encoder is a class. Within, where is it? SBERT.net, we have here the API of a specific class. And this class is the sentence transformer cross-encoder class. And what it does, you're not gonna believe it, it takes two sentences as an input, and it either predicts a score or a label for the sentence pair. So, could be the similarity or whatever you like. This is it. It has a specific training, a fit command that trains the model with a specific training objective, and it has a predict option. So we perform a predict with the cross-encoder on a given sentence pair. And please remember, we have here as an input a list of sentence pairs. So we have a list of sentences of pairs and another list of sentence pairs. So what we have 4 singular sentences as an input to this particular class of cross-encoders. So cross-encoders, what are they? BERT is a representative of this class of cross-encoders. Of course, we are running here SBERT, so BERT, of course, a cross-encoder. Now, both sentences are parsed to the BERT and network, and attention is applied across all tokens of the input. So at this time, both sentences are simultaneously passed to BERT, and this is why it's called cross-encoder. And both inputs are separated by a specific SAP separation token, and a multi-head attention is applied over all its tokens, of all input tokens, whatever is now your specific token. So, 2 things to remember. Cross-encoder do not produce sentence embedding. Cross-encoder produce an output value between 0 and 1, indicating the similarity of the input sentence pairs. This is it. And now we're gonna code. And as I showed you, it is a specific class, cross-encoder. So we just have from sentence transformers, cross-encoder, import our cross-encoder. And then we download a pre-trained cross-encoder. Everything is done. Imagine this beautiful. But not let's be too happy. Let's have a look. So the first indication tells us STSB. Now this is the STS benchmark dataset, and it comprises 8,628 sentence pairs. Now you have to know now the genre, because what I'm going to show you later is we do some domain augmentation. So you should know the content of your training data. And the genre here is news, whatever it captions, and a forum for discussion, open forum. And the time is about 2012 to 2016, maybe even 2017. This is the first part of our pre-trained model. It is trained on this benchmark dataset with 8,000 sentence pairs. Now the second part here, as you already guessed, is here our model. We have a distilled Roberta base model, and a distilled Roberta base is a distilled version of our original Roberta base model, of course. Our specific model has 6 layers, has 768 dimension, and has 12 heads, in total 82 million parameters, compared to the original Roberta 125 million parameters. Now remember, Roberta uses text tokenizer and here the byte pair encoding. I have an own video on this. Vocabulary size of 50K, and the input is taken in pieces of 212 contiguous tokens that may span over the documents. And of course, we are here masked language modeling. Now, contrary to our pure BERT model, the masking is done dynamically during our pre-training. So, everything is done. We just import, we download our pre-trained cross-encoder from HuggingFace. The nice people were so nice to do the training for us to define a model, use input dataset, SDS benchmark dataset, and define the cross-encoder for us. So we just now apply the cross-encoder. So we have, remember, a pair of sentences. So first pair is, the first half of the pair is the query. A man is eating pasta. My goodness, this is a highly complicated thing. And then we have all the other sentences. We want to pair with the first sentence to create a lot of sentence pairs. So the sentence combination is the query and the corpus sentence for the corpus sentence and corpus. So we have the sentence pair, a man is eating pasta, and the second part is a man is eating good food. The next sentence pair, a man is eating pasta, and then a man is eating a piece of bread. And then you remember. So we compute the similarity scores for this combination. Remember, we have now the model predict, as I told you, predict sentence combinations. And then we just sort it. And this is it. And let's do the calculation. So first is download the model. HuggingFace. Done. And then we have the query is a man is eating pasta, and then we have the cross correlation from our cross-encoder. And we have here numerical value, and it is sorted. So the highest numerical score with .67 is a man is eating food, is the best correlation to the query, a man is eating pasta. Beautiful. And then we have .34, a man is eating a piece of bread. And then we have all the other things, 0.0 something. So beautifully, this is good. This looks like it's working great. Two other notions you might encounter if you're working with data sets. GLUE, General Language Understanding Evaluation Benchmark, is a collection of 9 data sets for evaluating natural language understanding systems. And the famous SQUAD. And SQUAD stands for Stanford Question Answering Dataset. Provides a paragraph of context and a question. And the task is to answer the question by extracting the relevant sentences from the context. Beautiful. This is our cross-encoder. We used our cross-encoder API, and you see this is the simplest example if we have a pre-trained cross-encoder. Now, if you have some specific data set, you can train your cross-encoder yourself. But before we do this, I want to reflect on the strength of Bi-encoder. Now, remember, a Bi-encoder is typical SBERT. The sentence transformer, sentence BERT model, an SBERT model encodes each sentence independently and maps those sentences to a dense vector space. Again, the Bi-encoder maps each input independently to a vector in a dense vector space, in a topological space. Now, Bi-encoders are used whenever you need a sentence embedding in a vector space for some comparison. Applications are information retrieval, semantic search, or even clustering. A downside now of our SBERT model of cross-encoders is the extreme computational overhead for many tasks. So, okay, cross-encoder I showed you before here. The cross-encoder here has a downside, and the downside, or the negative, is extreme computational overhead for many tasks. For example, and this is now for some of importance, if you have 10,000 sentences, you have a quadratic complexity if you want to calculate it if there's a cross-encoder. And if you have a V100 GPU, you have about 65 hours of compute time. Now, if you on the other side have now our Bi-encoder, remember, Bi-encoder does something completely different. A cross-encoder gives us a sentence between 0 and 1, and a Bi-encoder gives us a sentence embedding in an n-dimensional topological vector space. So careful, don't mix up those two things. But we can combine a cross-encoder and a Bi-encoder for something beautiful. But we have to understand the benefit of a Bi-encoder. Now, the complexity of clustering 10,000 sentences is reduced from 65 hours with a cross-encoder to about 5 seconds with a Bi-encoder. So we gain speed. We have, with an SBERT Bi-encoder, a lower performance than a cross-encoder who does calculate the attention between each input token. Of course, it is really does everything to everything. But with a Bi-encoder, we just map it to a topological vector space. And another problem with Bi-encoders, and this is important, this will be the second part of the video, we will focus on this. Bi-encoders require substantial training data and finding over the target task to achieve competitive performance. Why? Imagine you have to fill up a swimming pool with water. And imagine the Bi-encoder gives you one droplet of water, one drop of water. And you have to fill up the whole swimming pool, the whole vector space, to be able to do calculations in this vector space, to be able to swim in the swimming pool. Because if you do not fill up more or less the space of this vector space, you don't know if there are significant holes in your vector space. Whole regions of this vector space could be empty. Every mathematical computation would be a catastrophe because the vector space is missing parts, you know? So you need huge amount of data. Again, Bi-encoder, lower performance. Bi-encoder computational really fast compared to cross-encoders, and they need a lot of data. A lot of data, and this is what we will do later on to generate such a vector space. So now we know the good things about a Bi-encoder and a cross-encoder and the bad thing of a Bi-encoder and a cross-encoder. Now, if we combine Bi and cross-encoder, so this means if we combine an SBERT with a traditional BERT system, with all the attention, with all the multi-headings, we can focus to do it in a way that we take the best of SBERT and the best of BERT. And one example here is retrieve and cross-rank. So you have here the task of information retrieval, or of semantic search scenarios, or of question and answer scenarios. And a cross-encoder with a Bi-encoder can be a very powerful tool. Let's have a look at this. We are here in the area of sentence embedding. And remember, cross-encoder here, sentence transformers, sentence SBERT if you want, SBERT here. Oh, have to go back. And here the cross-encoder. And this cross-encoder, you have a model, you have the labels, you have a maximum length, you have a device, CPU or GPU, you have an auto model augmentation and the activation function. And we're going to use this now to program our first example. So here we go. An easy example for retrieve and re-rank, or question and answer, whatever you like it. And we do an in-document search. Remember that a cross-encoder is good if you have not 10,000 plus sentences. So let's say we have here an in-document, and the document here is this, whatever it is, something here. Yes, I don't know how many characters it is, but this is our document. And we want to search in this document. So we split this article into paragraphs, and then every paragraph into sentences. So this is all it's done here. Then we combine, now for example, 3 sentences into what's called a passage. You can choose more than 3 sentences, less than 3 sentences, whatever. No problem at all. Gee, don't do this to me. The smaller value you choose, the context from the other sentences might get lost. And if you have a larger value, let's say 8 or 10, the more context for the paragraph remains, but the results are longer. In a question and answer, you get long results. And somewhere there is the relevant part. So let's choose 3. It's some middle ground. Or if you want to do for your example, choose 5. And check it out. Let it run. So, and then we say yes, 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 the window size, we do the partitioning if you want, and we have the paragraphs, the sentences, and the passages. Great. Now we have structured our input text in segments. Now, again, let's load our cross-encoder. There is a cross-encoder on HuggingFace, cross-encoder that has been trained on, you know this now, on a dataset. It's called MS Marco. The model itself is tiny BERT L2, and what it means, it's a BERT model, it's a tiny model. It has a BERT model with only 2 layers trained on the MS Marco dataset, so relatively shallow. But the advantage is it's quick, it's really quick, it's for demonstration purposes. Now, if you want to do some serious work, maybe you do not take the tiny, but you take a BERT medium or BERT large or whatever you prefer. And please be careful, whatever dataset, training dataset you choose, and the quality of the dataset, and the time that the dataset spans. If it's from 1995 to 2005, you will know nothing about the coronavirus, and so on. So, careful. Yes, 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 yes. And so here we go. Let's execute this. We have here some queries. You can have 1 query, or let's do 4 queries at the same time. How large is Europe? Is Europe a continent? What is the currency in Europe? And is Europe in the south part of the globe? Great. Highly intelligent queries. And now we say, okay, for the queries, we go for all queries, we run through this, and we have now a model predict, where we say we have 4. This is our query, and then we do here the other parts of the sentence to have sentence pairs. And then what we do is we simply calculate how close they are semantically correlated. We do then decreasing order, it's the output, and then we have some formatting, and this is it. So I would say, let's start. Let's do it. So we have 1 paragraph of text, yes. This is exactly what I showed you here. You download your book, your publication, your archive preprint, your scientific publication, but have a look at that it's below about 10,000 sentences. I mean, if you run on a cluster of GPUs, if you have some TPU tensor processing unit parts, you can go maybe a little bit further, but you have a quadratic complexity in compute. So in this 38 sentences, and if we group it together in 3, we have a passage given 3 sentences, so we have in total 13 passages. So, and here we go, question and answer. The first query, how large is Europe? And now, depending on how big your window was, how many sentences you include in one answer, you have either a short answer or a large answer. So first, we have a score of 0.73, so highly prominent score. As you can see, there's just 1 with 0.3 and the rest is 0.0 something. So, how large is Europe? The first answer it would give, although some of its borders overland, Europe is generally called status of a full continent, but it's a great physical size and the weight of history and tradition. Here we go. Now in the 3rd sentence, in the 3rd sentence we have now our answer. Europe covers about a million square kilometers, square miles, or 2% of the Earth's surfaces, or Jesus, 6% of the land area, make it in the second smallest continent. And then it goes on. Politically, Europe is something. So you see, if you have chosen, I don't know, this is just 38 sentences. If you have 5,000 sentences, you can have your query and you can get the answer in a different length. You can have a real length answer or shorter answer, whatever you want. And it is ranked for significance. Now, second query, Q2, is Europe a continent? And then we have, you see here, the score from our cross-encoder and our pre-trained cross-encoder. Here we go. The cross-encoder here is tiny BERT L2. So we have a tiny little BERT system with just 2 layers. Yeah, but it gives us a really good answer because they tell us, is Europe a continent? Europe is a continent located entirely in the northern hemisphere and mostly in the eastern hemisphere. It comprises blah, 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 and you have the number of sentences we defined. What is the currency in Europe? Well, then we have a lot of 000s, but one that sounds, okay, maybe the currency of most European countries in the European Union, the euro. Beautiful. This is the answer we're looking for. Is Europe in the south part of the globe? And you see everything almost is 0 except 1.43. Europe is a continent located entirely in the northern hemisphere. So, correct. This is exactly the question and the answer we're interested in if you have a longer answer sequence. And the answer sequence, as I showed you, you can easily define. Where are we? Here, defining the window size. And we combined up to 3 windows, 3 sentences in our window in a passage, and you can see smaller and larger files. So, beautiful. You see, we used here as a question and answer system, our cross-encoder. Now, of course, I told you you can train your cross-encoder, you can define your cross-encoder, you can have a cross-encoder on specific training data sets that are more suited for your training. Let's say you have a medical training data set, but remember, it has to be a labeled sentence pair data set for medicals, for astronomy, for beauty and the art, or whatever. And then you just take any, let's say, transformer model, a BERT model, with how many layers you like, and you can train this. And this is then a trained cross-encoder you can apply, and you see how easy it is to apply for a question and answer system. If you have, for example, here, a document search, or you have a publication. So now the second part I wanted to show you is, and it's already, well, 20 minutes into it. This is the last part. The rest will be the next video, is zero-shot classification. So what do we want? At first, we have to install our transformers because we need some transformer pipeline. Yes, beautiful. Satisfied. And then we go. And as you see, it is so easy. From the transformers, we import our pipeline. And from the pipeline, we say, okay, the task is a zero-shot classification. And then we choose a model. And you will not believe it. We choose a cross-encoder. We choose a cross-encoder as our model. And this model has been pre-trained on a specific data set. And please do always this. Have a look at the data set. You have here beautiful HTTPS link, HuggingFace.co datasets SNLI. And if you followed it, sorry. Oh yeah, great. Oh, come on. Come on. How stupid I am today. Unbelievable. Ah, here we go. Here we have HuggingFace dataset SNLI. And you just check it out. The SNLI corpus is a collection of 570,000 human-written English sentences pairs, English sentence pairs, manually labeled for a balanced classification with label entailment, with the labels, 3 labels, entailment. Yes, the sentences belong together, contradiction. Sentences contradict each other, and neutral. I don't know. This is it. And if you want to have here, you can have a plain text. You have the premise, the hypothesis, and the label. And then you have 570,000 sentences. My goodness. So the first is, this church choir sings to the masses as they sing songs from the book of church. The church has cracks in the ceilings. Now the classification, the relation between those sentences was labeled by some person as neutral, the label 1. You can agree with this or not. Just somebody sometimes classified this as neutral. Second, church is filled with a song, sing as they sing joy. Now, somebody, some human, somewhere said, oh, it's an entailment. Yeah, there is a correlation between those sentences, label 0. And then the third example is a contradiction. The label is 2. They sing to the masses, yes, 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 and a choir singing at the baseball game. So we have a different location, but we still have a choir singing, but they say, hey, this is a contradiction. Because if you just look at the geographic place, it's a baseball game and this is the church, this does not belong to each other. Well, in both cases, it's a core, so whatever. Somebody decided it's a contradiction. So here you see how good is my training data set. And please always, always check the quality of your training data set. And the other thing is, what time period does it span? Is it actual? Is it 5 years ago? Is it 10 years ago? Is it from another century? You have to make sure that you know everything about this. Read about this. There are beautiful descriptions about the data set. You have the premise, you have the hypothesis, you have the label, yes, 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 you have the splits. Yeah, the size, of course. You have a training data set, you have a validation data set, and you have a test data set already prepared for you. You see the biggest, of course, is the training data set, and then you have 10,000 sentence pairs for a validation, and then you have 10,000 sentence pairs for a test data set. Data set on the corpus, yes, different version, yes, includes content from the Flickr corpus, the visual genome corpus. Yes, yes, yes. Language producers, annotations, yes. 2015, we have some, okay, label, entailment. Social impact of the dataset, discussion of the bias of the datasets, limitations of the dataset. Somebody already looked at the dataset and told you what are the limitations of this dataset. Dataset curators, currently by the Stanford NLP group. And it was sponsored by this one. And then you have the citing information if you use this dataset. And here we have it, the year is 2015. So this is a dataset that was created 7 years ago. This is the citing information. So now you have the information about the dataset. Now we go back to our computing and we just found out about these 3 letters, NLI. That's all. Now the second part is, yeah, NLI, of course, is a sum of SNLI and multi-NLI datasets. Now, as the SNLI we just had a look at, there's 570,000 human-written English sentence pairs manually labeled, and the multi-NLI is a multi-genre, and this is now important if you have different domains, like physics, chemistry, mathematics, politics. Multi-genre is always good. Natural language inference corpus, and it was crowdsourced collection of 433,000 sentence pairs annotated with textual entailment information. So we take both of these corpuses, we have close to 1 million sentences, and this is just those 3 letters, and then we have the model, and this is the BERT based model. This is from Microsoft, a variation of BERT. Anyway, let's take it. We are already half an hour. So, and now we do a 0-shot classification. You might say, my goodness, how complicated can it be? And here we have it. This is it, 4 lines. So, at first you have the sentence that you want to have analyzed. And as Apple just announced the newest iPhone 14. And then you say, hey, I want a classification, and you define what you want. No? You say, I want technology, religion, politics, phone, tablet, and computer. And you can say, you can insert whatever else you want. So you have your sentence and you say, adjust this sentence to a classification I provide you with. And then you say, classify. the sentence, and the labels. And this is it. Print the scores. Let's do this. Real time, online, done. So classifier, this is the only thing that we use here that was predefined. Our classifier is simply the pipeline. Oops, here we go. Come on. The classifier, here we go, is our pipeline from a zero-shot classification, and we use this cross-encoder model. So you see, cross-encoder are really powerful things in SBERT. They're a class in SBERT that we can use to do a lot of interesting things. And this is just the introduction to the main topic that will be part of the next video, as I just found out. Now, if you look at this, so this is a sentence A, then we have a sentence B, and I say now something from politics. The Democrats are fighting against the Republicans. And I say, is it religion? Is it sport, politics? I have here war, so really fighting, because I say here fighting, so I say war. Or is it just a confrontation? Is it an enjoyment? Is it mass hysteria? I have no idea if mass hysteria exists as a label, but I just inserted it there. And then the sentence C is, Jupiter is a planet in our, in our solar system. And I say sports, politics, alchemy, science, astronomy, astrology. And I say, this is my 3 sentences. So let's calculate it. 1, 2, 3. This is real time on my little laptop. This is calculated here on my laptop. And you see how fast it is. So, but there's now a problem. If you look at the scores, you see, this is strange. We have dot 36, dot 31, dot 30, and then is dot 00 something gone. So the first 3 are really there. Technology, religion, politics, and I think, no, Apple just announced the iPhone 14 is nothing about religion, nothing about politics. And I say, maybe it's a mistake. So I check out the second. The Democrats are fighting against the Republicans, so clearly politics, and I get dot 5, dot 36, dot 00. So the first 2, religion and sport? No, it's politics. And even worse, because now it's science. We have sports, politics, and they give us what? Sports? Dot 49? But then relax. Relax, I made a mistake. So if we just print the scores of this dictionary, we are missing that the dictionary itself has been sorted already by a classifier. So if we now take the sentence A, Apple just announced the newest iPhone 14, and we print the labels and the corresponding scores together, we see, and this is always when you see here a set of numbers, and you have it declining, and you have here declining numbers, continuous declining. This is an indication that there has been some sorting done internally. So be careful, because now you see, originally as I defined technology, religion, politics to be the first 3. But now in the dictionary, the result was technology, phone, computer to be the first 3. There we go, you see? So, and now it makes sense, because now if I look at the first 3 scores that are above dot 00 something, I have now most significant, it belongs to technology, it belongs to phone, and it belongs to computer. And now this is the right answer. So even if you use this 0-shot thing, don't make my silly mistake that I just look at the scores. You have to read out the labels of the system, because maybe the classifier rearranged the numbering, no, the dictionary. And then you really think, hey, the system is not working, but it is working beautifully. Here, tablet I inserted for a reason. A tablet, it could be a tray that you present some apples, that you bring some food to somebody, that it is an Apple tablet. I mean, Apple itself is a fruit, but let's talk about a computer. It's a tablet, I don't know what's the Apple tablet sub-nomification. And as you can see, tablet in position 4, 1, 2, 3, 4 has 00 something. So this is not recognized as a computer tablet. Computer is recognized by tablet here, the classical form from household in the kitchen. is stronger and overrides the maybe computer notation. So interesting to see this. Now, the second was the Democrats are fighting against the Republicans. So what is this? Let's look at both the labels and the scores. And the labels you can see A, highest, it is a confrontation, yes. And you remember I said also war. Is it because fighting against, this is typical lexical search and not semantic search, would give you, hey, this is an act of war. But no, it understands that it primarily is a confrontation. Then it understands its politics. And then it comes with the lexical connotation of war. And if you look at the score, you see that only the first two scores are of significance. So it is a confrontation in politics. And these are the score for this. And for the rest, you have 0.0. This is 0.0, so forget about the rest. So you can forget about everything here. But even here would give you a ranking, you understand, because I said fighting for war seems reasonable. Now, mass hysteria was then ranked religion even and sports, and say, no, these two parties are not doing any sports at all. It is 0.001, so forget it. And the last sentence, the sentence C, Jupiter is a planet in our solar system. We now calculate, here we are, now with the labels and the scores, and we say, at first it's science, then it's astronomy. And these are the first, if you look at the numerical indicator, this is .4 and .3, so these are the only one that are not .0 something. So they're only the two first are significant, science and astronomy. And then, of course, in astrology, which is, of course, nonsense, but there's also Jupiter. And there's also what I was talking about, Jupiter. Jupiter is a planet in the solar system, and they use Jupiter for something. Okay, so then and then sports, alchemy, politics is no, and no. So you see, zero-shot qualifications, which we were looking for, are great if you use a transformer, if you use a pipeline for the task of zero-shot classifications, and if you use a pre-trained cross-encoder. And somebody was so nice to do all this pre-training for us, for the cross-encoder. And if you think that this is just, my goodness, close to 40 minutes, and I mean the introduction. And if you think that's the only cross-encoder, no, it is not. Because let's go back to HuggingFace. Let's go here and say cross-encoder. I don't see my things. Cross-encoder. How many cross-encoders do we have? We have 29 pre-trained cross-encoders ready for us that you can use them. You just can download them and use them. And here, 12 layers, 38 dimension. You have NLI, Roberta small, base, tiny L4. Roberta base, is there a large? Come on, where are the large one? The really heavy one. Yeah, here, for example, 12 layers, version 2. Oh, here, Quora, Roberta large, distill Roberta base. STS benchmark Roberta large. Yeah, this is nice. Let's take this one. And you see it's a cross-encoder for the Quora duplicate question detection. And we use here the class of sentence transformer cross-encoder. This model was already trained on the STS benchmark dataset. I show you how many input there was in this. And so you can find for the right training dataset. Here, the training data, you see this is the second heading already, the training data, what it was trained on, STSB. And then comes the model and the size of the model. So find the right training data for your domain, science, gossip, everyday, whatever you like. Then choose a model with the number of layers, with the number of hidden dimensions. Is it BERT, Roberta, whatever, distilled, a smaller version, just 2 layers, mini, tiny BERT, whatever, the large version in, I don't know, 1024 hidden dimensions, whatever. Find the perfect pre-trained dataset, the dataset for you, the model that it was pre-trained on, and then you have a cross-encoder, and this cross-encoder is gorgeous. And No, we are at 40 minutes. I have to stop here. Next video, I show you a little bit more complicated example, an advanced example, how we perform re-ranking with a cross-encoder for semantic search if we have a mighty text. And then, after I've shown you this, we finally come to the main part of the video that I showed I would do 5 minutes into this video, but it will be in the next video. The cross-encoder will serve as little booster rockets. And what we want to do, we want to optimize our SBERT system. And we need some domain augmentation. So the cross-encoder will do the domain augmentation for us. And then we have a new SBERT model we can train in a supervised way that we can start the turbo engine on our SBERT model. But this will be a little bit more complicated than this introduction. I hope you enjoyed it. Please remind yourself that I will have to start here after the zero-shot classification next time. And yeah, of course, if you want to use the same model, yeah, I'll show you this one, no problem at all. Since you are still with me, you get a bonus. So here we go. The same model we used for the zero-shot classification, you can use also for sentence pair similarity. So very easy. We have our cross-encoder. Our cross-encoder is absolutely the same cross-encoder we just had in the zero-shot example, the NLI BERT base model. And then we just say this is our model, and then the model predicts. And remember, right at the beginning, I told you you have to have 2 sentence pairs. And the first sentence pair is a man is eating pizza and a man eats something. Sentence 1, sentence 2 of our sentence pair. And since we have to have a list of sentence pairs, plural, we have here the second sentence pair. First sentence in this sentence pair is a black race car starts up in front of a crowd of people. The second sentence in the second sentence pair, my goodness, is a man is driving down a lonely road. And now guess which of those sentence pair is related and not. And of course, the first is related. There we have an entailment, yeah, so they are somehow correlated. And the second sentence pair of sentence 1 with the black race car and a man is driving down a lonely road is not related, or as they call a contradiction. It's a label that tells me, no, it's not correlated. And you see, this is the model, this is the predict function, and this is it. The label mapping is this exactly. We have here no, yes, and neutral, 0. We have defined a level for all parts. We just print the levels, and this is it. Again, we run it in real time. You see, it takes about 1, 2, 3, 4 seconds. We have the cross-encoder model, pre-trained model downloaded from HuggingFace, applied to our sentence pair. The model does the prediction. Easy, beautiful, fast. So this was it for cross-encoders. And if you are still with me, you get a second bonus. You get a preview of what will come. Because what we will do, we will use a cross-encoder and a Bi-encoder. Very easily. And we will have an example where we perform a re-ranking with a cross-encoder for semantic search. And at first, we use an efficient Bi-encoder to retrieve similar questions from a dataset. And then we re-rank the hits from the Bi-encoder using a cross-encoder. So we combine BERT and SBERT in an intelligent way, and I'll show you the code how it is done. See you next time.